Can you survive Jupiter? Only 1% escape the station.
Jupiter's station is falling. The hull is tearing apart. If you can hear this, you are the last survivor. Wake up, or die with us. Systems are failing. The reactor core is going critical. Get to the control room, now! Through the corridor. Move, move, don't look back. Reactor lockdown active. Enter the stabilization code to prevent a total meltdown. Complete the sequence. 2, 4, 8, 16. What's next? Is it A, 24, B, 32, C, 20, or D, 64? Hurry, time is running out. Solution. The sequence progresses by doubling each number. Each value is exactly twice the previous term. 2 times 2 equals 4. 4 times 2 equals 8. 8 times 2 equals 16. Therefore, 16 times 2 equals 32. Reactor stable, but we're losing orbit. Get to the bridge, now! Run through the transit tunnel before the gravity wells pull us in. Go! We need to align the station to clear the asteroid gap. Our current orientation is 45 degrees, but the target vector is at 180. How many degrees do we need to rotate? A, 90 degrees. B, 135 degrees. C, 180 degrees. Or D, 225 degrees. Make a choice. We're running out of time. Target locked. You nailed it. By subtracting our 45-degree offset from the 180-degree vector, you found the exact rotation of 135 degrees. Station alignment is now stabilized. The main computer is back, but the cooling matrix is down. You have to divert the emergency coolant flow manually from the upper deck. The quickest way is through the hydroponics bay. Watch your step. The atmosphere in there is becoming unstable. You found the terminal. Good. Look at the alpha tank. It's at 20%. To trigger the emergency oxygen spike, we need exactly 3 times that dosage. Calculate the percentage and input the correct value. A, 30%. B, 40. C, 50. Or D, 60%. Hurry. The whole deck is destabilizing. Perfect. 3 times 20% is 60. Oxygen is back. Now listen, the power grid is failing. Get to the power hub and reroute the energy to the hangar, or the pods won't launch. Move it. Get in. The lift is the only way to reach the lower power grid. The central computer is already losing sectors. There, the terminal on your right. Access the distribution matrix. We need to reroute the remaining energy to the hangar pods. Move. You have one large gear with 60 teeth, connected to a small gear with only 20. To move the arm, the large gear needs 1 complete rotation. Calculate how many rotations the small gear requires and input the correct value. A, 2, B, 3, C, 4, or D, 5 rotations. We're losing power! Copy that. 3 rotations is the exact ratio. Gear B is 3 times larger, so your calculation was spot on. The lift arm is moving and power is stable. You've unlocked the next subdeck. Great job, cadet, but stay sharp. The core is still overheating. Wait for my signal. Move it, cadet. Through the service tunnel and past that bulkhead. The hangar is right behind that door, but hurry. Containment is failing, and I can't hold this path open much longer. Go, go, go! Cooling grid critical. 1,200 liters total. Sector A takes half. Split the remaining half equally between B and C. What is the load for Sector B? A, 600. B, 400, C, 300, or D, 200. Input the value now or the core will blow. Excellent work, Cadet. I knew I could count on you. 300 liters is the correct answer. The logic is simple. With 1,200 liters total, Sector A, being the hottest, absorbed exactly half, which is 600. The remaining 600 liters had to be split equally between B and C. So, 600 divided by 2 is 300 each. The flow is perfectly balanced and the core temperature is dropping. Great job. Keep moving. The life support sector is just ahead through the main service corridor. Don't stop for anything. The air scrubbers are failing and the pressure is spiking. Get to the main terminal before the whole deck loses oxygen. Go, go, go. Damn it, the pressure's still rising. Look at the monitor, Cadet. Tank A is redlining at 500, and Tank B is stalling at 200. We need to find the exact equilibrium to stabilize the life support. How many units do we need to transfer from A to B to balance them perfectly? Is it A, 100 units, B, 250 units, C, 300 units, or D, 150 units? Choose now, I'm losing the seal on this room. Spot on, Cadet. Exactly 150 units. Taking 150 from Tank A leaves it at 350, and adding them to Tank B brings it up to 350 as well. Perfect equilibrium achieved. Pressure is stabilizing, but the blast triggered a total lockdown. The hangar bulkhead is sealed, and the neural link code is scrambled. We need to move. Almost there. Keep moving. The hangar bulkhead is open. We can't let it cycle shut. Look, once we cross that first portal, the escape pod is right there on the right. There. That's our ticket out of here. Get inside, Cadet, quickly. Get to the console and prep the ignition sequence. This is our only way out. Cadet, listen to me. This is the final challenge. If you don't input the correct vector, the POD will never release and will be trapped here. Look at the neural link monitor. The question is clear. Thrust vector calculation. The deviation must be equal to 3/4 of a right angle of 90 degrees. What is the correct input value? A, 67.5 degrees. B, 45 degrees. C, 75 degrees. Or D, 135 degrees. Choose fast and hit enter. We are out of time. Calculation validated. To determine the correct thrust vector, we had to find 3/4 of a standard 90-degree right angle. By multiplying 90 by 0.75, we get exactly 67.5 degrees. This precise angle allows the escape pod to clear the docking clamps and exit the hangar bay without structural collision. All systems are now green. Launch sequence initiated. You did it, Cadet. You're clear of the station, but don't celebrate yet. Look at the void ahead. The real challenge starts now. Can you actually survive out there? We're about to find out.